Okay, we are live.
Okay. Good morning, everyone. I am Abhishek Roy, Assistant Professor of the Department of Civil Engineering, Meghnad Shah Institute of Technology, along with Professor Saurabh Pal of our department, will conduct today's webinar, which is on Spectrum Civil Engineering today. I, along with Professor Saurabh Pal, take the opportunity to welcome you all on the behalf of the department. Now, I request our HOD sir to give the introductory speech. Sir.
Thank you, Abhishek.
Hmm.
Hello, everyone. Myself, Professor Sheikh Hasim, Head of the Department of Civil Engineering, Meghnad Institute of Technology. A very good morning to all of you, and welcome to today's session of our webinar series. The Department of Civil Engineering, Meghnad Institute of Technology have launched a webinar series since 4th August in the name of Spectrum Civil Engineering today. It is our third week, and our objective to arrange such a webinar series to introduce the updated and modern techniques in the different civil engineering field beyond the curriculum in this pandemic situation. And we think it is very essential to reach all of the civil engineering students for in these situations. First of all, I want to welcome to our organizing committee members, especially Professor Priyabrata Guho, Professor Saurabh Pal, Professor Abhishek Roy, Professor Sagota Bisoi, Professor Seth Thakur, who are working day and night to organize such an essential and wonderful webinar series. And I'll welcome all the other members who are working from the behind for successful conduction of this series. I would like to welcome and thanks to our Honorable Principal, Sir Dr. Ankur Ganguly, for his extreme help and support from all respect, without which we cannot reach at this level. So we told, as we told every time, that we will bring to you different experts from academic and industry in this platform. Today, we have Dr. Arindam De with us, Associate Professor, Department of Civil Engineering, IIT Guwahati. I heartily welcome to Dr. Arindam De from our department to come here and agree to spare his valuable time apart from his busy schedule. Thanks to Dr. De again. And Sir offering a wonderful topic, blending theory and practice in geotechnical engineering. So hope you will learn something extra from him in the field of geotechnical engineering, and participants will get benefited from this lecture. I welcome to all participants to join here for this season. If you have any query or specific questions during the lecture, you please type them on appropriate place mentioned by our executive members. They will touch with you and they will help in this regard. We will bring them and bring all the questions to our honorable speaker at the end. Thanks again to our organizing committee members, and thanks to all of you. Hope you will enjoy the session. And I had like to request Professor Abhishek Roy for conducting the rest of the session. Thank you, all of you.
Thank you, sir, for such an introductory speech. Now, I am requesting Professor Biswajit Thakur, Professor of our department, to introduce our guest speaker, Professor Arindam De.
Good morning and welcome everybody. This webinar series Spectrum Civil Engineering today has reached the third week, and we are delighted to have Professor Dr. Arindam De from Indian Institute of Technology, Guwahati, amongst us as our eminent speaker. Today's topic that Professor De is going to deliver is blending theory and practice in geotechnical engineering. Dr. Arindam De is currently an associate professor in the Geotechnical Engineering Division, Department of Civil Engineering, Indian Institute of Technology, Guwahati. He obtained his bachelor's from Jadavpur University, Kolkata in 2003, followed by his MTech in 2005 and PhD in 2009 from IIT Guwahati. Before joining IIT Guwahati in 2011, he has been a postdoctoral fellow at the Strega Laboratory, University of Molise, Italy. He works in very varied fields of geotechnical engineering, including foundation engineering, geotechnical earthquake engineering, geotechnical investigation, computational geotechnical stability, and landslides. His current research group includes 8 PhD students and 2 MTech students and has already supervised 7 doctoral research and 22 MTech students. His research group has more than 250 technical contributions at international and national journals and conferences, seminars, including book chapters and technical reports. He is a member of several professional bodies, including ISSMG PC 208 Committee on Slope Stability and Landslides, IGS, PRG, Institute of Engineers India, and Forum of Scientists, Engineers and Technologists. He has received several research awards and has been an active research consultant in the area of geotechnical engineering. Apart from this formal introduction, Dr. De has been my immediate junior in Jadavpur University. He is like a brother to me. Of course, having him in MSIT Civil Engineering Department, a sort of homecoming for him also. Dr. De, the session is yours now.
Okay, thank you. So first of all, a very good morning to all of you. I guess everybody is doing best possible at these distressing times. And I would like to thank the organizers first to give me the opportunity to be a part of Spectrum. And it was like in this distressing time, I made a vow to myself not to burden anybody with such online webinars. But then I got a call which I could not refuse. So Dr. Thakur called me up, and then it was all a yes and go from my side. So good morning to all the participants for this particular webinar. And I hope everybody is doing fine. And we will go ahead with the presentation, what we have scheduled for this next 1 hour, 20 minutes or so. I hope everybody can see the presentation which I am sharing.
Yes, sir, it is visible.
Okay. So to start with, today we are going to talk about a particular field in geotechnical engineering where we actually bring together 2 different fields. One field belongs to the theoreticians who does work in pen and paper, and the other part belongs to the practitioners who does their job in the field. And we take up the topic today where we blend this theory with practice in geotechnical engineering. To start with, this theory and practice are like the signpost at the crossroads. They stay together. They do not like to look at each other. So always there is a big brawl between the theoretician and the practitioner where no one wants to really budge. So everybody has their own viewpoint, everybody has their own statement, and each do not think too accommodative of the other. It's like that angry couple who has to stay together but will not talk once a brawl is out and will not face each other, but still will do the work which has to be done. Now, when we
talk about the genesis of this particular dissatisfaction between theoretician and practitioners, this genesis actually is a long one. So the theoreticians mostly believe that when they do something in theory, when they put it into pen and paper, exactly the same thing is going to be replicated in the field. So they say in theory, there is no difference between theory and practice. However, when you go to the field, in practice, actually there is the difference. So something which works out in theory is not going to help in practice, and something which is working in practice has to come back to theory. In WhatsApp or in the social media, a very fun post many times gets circulated. It's a worth post actually, although it's a fun post. So theory is when you know everything, but nothing works. So you put down everything in pen and paper, do all the design analysis, and in the field suddenly you see it is not working. Practice is when everything works. So you erected a structure in the field, it is all standing, but we really don't know why it is standing. And then we have our labs, which says we combine theory and practice, nothing works, and no one knows why. The issue is that the theory and practice, although being at the signpost at the crossroad, in reality, they have to be like this, entwined with each other to set the bigger picture of learning. So that's where this blending is necessary, and it is what we have to do. When we talk about blending theory and practice, once you come inside this circle, it is actually a never-ending loop. Whenever in our daily life we see something, we observe something, we note down our observations, whether in pen and paper, whether in thoughts, whether consciously, whether unconsciously, we note them down. And then we start thinking of interesting questions. Why did that happen? How did that happen? When did that happen? All those WH questions we put forth. And then we look again. We start recognizing some patterns. We start recognizing some chaos. We start formulating some hypotheses. That what can be the general phenomenon for which such a thing is occurring? Then when we put forward the hypothesis, we try to develop testable predictions. Okay, so I put forward my own hypothesis that a bird is flying from left to right. Does it do each day? So let me predict that tomorrow also this bird will fly from left to right, but it did not happen. So we start gathering data to test the predictions, and we try to recognize when does it match, when does it not match, how much is the deviation, and based on those collected data, we refine, alter, expand, or even reject our hypothesis. That's not the end. We do all those modifications and then again develop that testable prediction. So basically what we do, we form a subloop here as long as we are not satisfied that our formulated hypothesis is matching with the testable predictions. And when it does match, we go to develop the general theories. And once we develop the general theories, again we start making the observations, which paves the way for further modification of the developed theory. So this becomes a loop where once we enter, we do not come out, we just go on modifying each and every member of the loop. In today's world, when we talk about the different type of works involved, generally we classify in three categories. It can be a theoretical work, where you jot down all the equations, solve them up in order to satisfy some of the theory. You do the experimental investigations, be it in the lab, be it in the field, and you see how does the experimental investigation and the theoretical simulations represent each other. And of course, you have the computational part where you go beyond that particular closed form theories and try to see new vistas. Now, practice is basically the union part of all these three Venn diagrams. So in this particular case, practice has to bring all these three components, and practice has to contribute to all these three components as well. Let us now look at a typical geotechnical project, since we are talking about blending theory and practice in geotechnics. So in any typical geotechnical project, we will always have a construction site for some particular work, and there will be some work being done: excavation, digging, soil investigation. Whatever infrastructure project is being laid at that particular construction site, the basic feature is that we always collect soil samples from that particular site and send to the geotechnical laboratory for testing, because that forms our crux of the knowledge parameter. So once these are sent to the geotechnical laboratory for testing, various type of tests are done to identify the soil properties, and these soil properties are then passed on to the design office for design and analysis. All this being done, then it is again brought back to the field for implementation along with the design details. But the issue is that once you bring these design details in the field, again many new sort of problem emerges which were unprecedented. Again we go on through this loop. So this particular loop typically represents a geotechnical project again, where we stop when we reach a desired level of satisfaction. Everything is not satisfied to the ultimate extent. Now, once we talk about geotechnics, so the ultimate aim is basically to help creation of infrastructures. What are infrastructures? These are basically anything and everything which can enable, sustain, or enhance societal and economic living conditions. So it is basically anything and everything which comes to help our daily living and daily sustenance. It includes various vistas. We have beautiful townships. We have beautiful bridges connecting one part of the land to the other. We have these transmission towers in difficult terrains carrying the electricity from very far away places to serve the society. We have intricate network of roadways and railways which serve as the mode of communication for all of us. We have the tunnels where we try to cut through the difficult terrains and shorten our communication paths. And as well as we have the dams and reservoirs which help in irrigation, hydropower, and all other various power sector aspects. These are only few of the infrastructures I have mentioned. Now, these infrastructures can become marvels when we pay proper attention to geotechnical engineering. And there are ample examples of such marvels. And these did not become marvel in a day. It started from the scratch and then got converted to marvels as of today. So geotechnics are the basal foundation to create marvels of infrastructure. Some example: Kansai, the floating airport. We have the twin tunnels through the Apennines in Italy. This is the foundation of the Burj Al Khalifa Tower. One can easily recognize the Palm Island, and we can also easily recognize the Hoover Dam. These are some of the marvels, and innumerable number of them are existing in our world. And we should really thank geotechnics for that, because everything started from the ground or with the ground. However, the point of caution, if we are not again paying attention to geotechnics, if we are not really blending the theory, what we are doing in our offices, to the actual practice, whatever is done to construct such geotechnical structures and marvels, unprecedented or catastrophic failures can also do happen. To see a few, the earthquake related failures of our communication modes of road networks, Huge landslides, maybe due to natural or man-made causes. Failure of dams, which is immensely catastrophic. This picture is a failure picture of the Teton Dam. Liquefaction-induced failures. This is a very famous picture from the Niigata earthquake. The seismic destruction of the building infrastructures. The Showa Bridge failure, again from the Kobe and Niigata earthquake. The failure of the retention system, wharves, protection structures in the seashore. This is a picture from the Haiti earthquake. This is a picture from Cuba. And we have also such failures which actually after failure has turned to a marvel. The greatest example is in front of us, the Leaning Tower of Pisa. So when we look into all these aspects, we can easily understand that geotechnical engineering is not only about the classroom taught soil mechanics and foundation engineering. It starts from that, yes, and then we progress through different sectors. So there are various vistas of geotechnical engineering: geotechnical and geophysical investigation, shallow, deep, and hybrid foundation. It may be on the horizontal grounds and slopes. We have very difficult subsoil condition where we need ground improvement for construction. Soil dynamics and earthquake geotechnics are a huge field where we look into ground response, liquefaction analysis, along with soil structure interaction, which is a very emerging and hot field in geotechnics right now. The pertinent problem of landslides, be it rainfall, be it seismic, so landslide hazard, along with slope stabilization. Geosynthetic engineering, reinforced soil structures, forms the basis of many stabilization projects nowadays. We have the earth retention system, whether rigid, whether flexible. And as shown earlier, a very important part forms the pavement and railway geotechnics, and never forgetting the dam and embankment engineering, which basically serves our sustenance and the power. So today, we will talk about 4 modules out of this in brief. One related to geophysical investigation, one related to ground response analysis and liquefaction evaluation, one related to rainfall-induced landslides, and one related to ground improvement of soft soil using PVTs. Each of these topic we will take in very brief, because each of these topic has come out with several PhDs. So you can understand the extent of research involved, but we will restrict to very brief. However, the interesting thing which I would show is that we will discuss some basic fundamental theories which are involved with each of them, and how it is getting related to some practical projects which we were involved with, and I will show them in succession. So we will take up the first topic, geophysical investigation through MASW. We will come to this MASW in a short while. Some of you might be already knowing or already have knowledge about this particular issue. Whenever we do these investigations, so geotechnical investigation or geophysical investigation, the target is subsurface characterization. We try to find out the intrinsic or the extrinsic geotechnical properties, and there are huge bunch of them, and we categorize them. So to show a few, we have the index characteristics. So we characterize the index properties: specific gravity, water content, PSG, relative density, consistency index of various type of cohesionless and cohesive soils. We find out the hydraulic characteristics, where we try to find out the permeability, the hydraulic conductivity. In the unsaturated domain, we find out the soil water characteristic curve, seepage through various porous media, all these things. We have the strength characteristic, where we find out the shear strength behavior, shear strength parameters, stress, strain, time, behavior, each of these pertinent issues. We also find out deformation characteristics, where we characterize the soils through stiffness, we have our compaction and consolidation characteristics included in this as well. We have the dynamic characteristics of soil. Whenever earthquake is involved, the static soil properties or monotonic soil properties will not suffice. They are starting point, yes, but we need to know the dynamic characteristic of the soil, how the soil will behave under the subject of wave propagation, seismic motions, and how these dynamic soil properties are required to understand them. We have some special characteristics as well. We try to find out electrical characteristic of soil, thermal characteristic of soil, magnetic characteristic, depending upon some specific project and specific requirement. Now, to do all these, we need investigations for soil properties, experimental investigations, which we can carry out in the lab, which we can carry out in situ, in the field as well. Several lab tests are available. You might all have gone through these type of lab tests in your UG, PG, and in your research curriculum. So we have sieve and hydrometer test, density index, Atterberg limit for the consistency, for the index properties. We have the permeability test under saturated and unsaturated condition, strength test, direct shear, triaxial shear, simple shear, torsional shear, compaction and consolidation tests. And for dynamic, we have the cyclic shear test, resonant column test, Bender element test, and several others. In the in situ, the most common is the exploratory boring. So you go to the field, drill a borehole, take out the samples, and find out the properties. Along with that, we have the field test as standard penetration test, SCPT, DCPT, DMT, pressure meter test, and several others. The issue which I want to highlight at this point is that whenever you do these investigations, if you are doing laboratory test, you are basically bringing some soil sample from the field and testing it in the laboratory, or in the in situ test, either you are drilling a borehole or you are pushing some sampler or some apparatus inside the soil to find out the in situ properties. What happens in both these cases is that none of these properties which you find out are for the undisturbed sample. Whatever level of expertise you have in sample collection, always the samples will be either disturbed or in a quasi-disturbed state. So we want to devise some technique through which we can understand some characteristics of the subsurface, but in an undisturbed condition. To come to that point, first let us look to the exploratory boring, which we call as representative exploratory boring. Why representative? We'll come to that shortly. This is the most common method to identify representative subsurface stratigraphy and to collect representative soil sample. Let us see one picture. Let us say you have a site, you have some project plan in mind. Based on that project plan, based on the codal provisions, you have to do some exploratory borings in the site, and you do at certain specific locations, collect the soil sample from there. Each of the borehole try to show you the geological or morphological profile at the site, and then when you connect all the boreholes, whatever you have done at the site together, you come up with the subsurface stratigraphy, as you can see in this particular picture. Issue is that these are representative. Why? Let us see through an example. Let us say there is a project site where it is decided that 6 to 7 boreholes will be done at certain spacing, whether uniform or non-uniform, and then we try to identify the soil profiles. Let us first concentrate at this particular part where you can see a soil strata ending in between two boreholes. Now, if this such discontinuous stratum exists, borehole done at particular spacing might not give you the proper idea where that particular soil strata has ended or where it got terminated. Although one of the borehole may give you certain engineering properties of the soil data when you collect the sample and do the test. Similarly, if you have an undulated trail, so let us say this red line is an undulated trail of some geological feature. Now, since there are sparse boreholes through which we are trying to locate this feature, we will get only few points in this borehole, and when we try to plot that feature, it may come up quite different than what it actually is. So that's why we say these are representative and does not actually conform the representation of the continuous subsurface. We will see one more example where we put forth the exploratory boring versus geophysical surveys. One point we also have to acknowledge that drilling and boring is excessively costly. So you cannot just go on doing boring, you have to do it with certain guidelines. Let us look at this particular picture at the top. So we have a particular soil site having two strata with an undulated interface. Now let us say we are doing the exploratory boring. We do at two places, one on this right hand side. We find out this interface point. On this left hand side, we also find out this interface point. And then we try to predict what is the soil strata interface. We land up in this linear interface in this particular case. Now, if you are using this site for some construction purpose, for important structures, and you pass this information to the design office, the design which may come out can be subjected to quite a catastrophe because the recognized interface or stratification is not what actually it is. So what is the way out? Should we go on doing the borehole drilling? Not possible. We have to do some trade-off. That's where seismic surveys come into picture. Now, seismic surveys are a group of survey where whatever we do to identify the subsurface is done from the surface itself. For example, in this seismic survey, we are using some wave propagation based technique. I'll come to this point later, what happens. So here we have a bunch of receivers. On the left hand side, we have a hammer striking on the ground on a striker plate. This generates the waves, passes through all these strata, gets collected in the receiver, and we do a series of analysis to find out what is the subsurface profile. Now you can well appreciate that this subsurface profile which we found out from the seismic survey is way better than what we have done from the borehole survey. In this point, one notion which comes to many, then we can eliminate doing this borehole survey. We can simply do seismic survey and find out the things. Well, it's not correct, because when you do exploratory boring, you get the soil samples, which is also needed to find out the index, engineering, and all other properties which I showed earlier. However, in the seismic survey, you actually get the idea how the substrata might vary, and thus these seismic surveys are not replacement surveys. We have to keep that in mind. They are complementary surveys, so they have to suffice with the borehole survey as well, because the borehole survey will give you the soil sample with the engineering properties. So how does seismic survey help? Once we know the substratification, then we can actually use the profile from the seismic survey to find out where we can actually drill the boreholes to get as much as information of the soils with minimum effort. Now, there are various types of geophysical survey. We call them as NDT, non-destructive test. We are not destroying the soil fabric. Whatever we are doing is from the surface. We have electrical resistivity tomography, where we use the dielectric properties of the soil using some anodes and cathodes on the surface. We try to frame out the moisture content and dielectric variation. We have magnetic resonance, whether nuclear or proton. It is governed by the magnetic minerals or magnetic constituents present in the soil elements. We have the ground penetrating radar, so you can think it of more as a sonar, where we try to detect buried structures by recognizing the reflected signal from the transmitted signal. And we have bunch of seismic refraction and seismic reflection surveys, which is more or less similar in principle to the ground penetrating radar with a different perspective. What we are going to talk here today is a bit advanced topic, that is MASW, multi-channel analysis of surface waves, which is basically used to identify the variation of the ground stiffness. We can do it in one-dimensional, two-dimensional, or three-dimensional formats. So this is a representation of MASW. As I was showing earlier, we will have a bunch of geophone, which we lay down in one particular array, whether linear, whether in different structural orientations. We have a hammer where we strike the ground with the hammer and the waves are generated, passes through different soil strata, get collected in the receivers. We do a bunch of analysis. I will tell that in a short while. And we find out the subsoil characteristic in terms of the shear wave velocity. So we get the shear wave velocity profile of the soil. Why is it called 1D MASW, one-dimensional? In this particular technique, we say that whatever shear wave velocity profile you are getting is obtained at the midpoint of the receiver array, and whatever stratification you are getting with the thickness of each layer and the shear wave velocity of each layer, we consider that the entire region of the soil is stratified and horizontally layered. So there is no undulation in the lateral direction. That's why we call these as 1D MASW. This is an assumptive one. That's not true. So we always have undulation, subsurface interactions within the soil. So what we have is the 2D format. Now 2D format is actually no big deal. It is like a series of 1D formats clubbed together. So what we do in 2D MASW, again we have a series of geophone or the geophone array. We do the test at a point. We will get the 1D profile at the midpoint of this array. Then we will move this entire array sidewise with certain guidelines which is prevailing with some overlap. We will get a new position of the shear wave velocity profile at the midpoint of the array of the new shift. We will repeat this process and we will go on collecting the 1D MASW profiles at each position of the array at their corresponding midpoints. This process is called a roll along mode. So we go on shifting the geophone array with certain overlap. How does it help? Once we get such 1D profiles for various locations, we do a cubic spline interpolation or any sort of image clubbing, and then we get the stiffness map of the subsurface in 2D profile, where you can see that what we were considering in 1D as laterally homogeneous is no longer so. It is heterogeneous in both along the width and along the depth. So we get a picture of the soil profile. 3D MASW is basically the same. So you do this overlapping, you do this roll along mode in the longitudinal direction as well. And then what we get is the variation in Z direction, variation in X direction, variation in Y direction, clubbed all together, we get the 3D subsurface profile. I said at the very beginning that we find the variation of ground stiffness, right? But what we are finding is shear wave velocity. So how does stiffness is further evaluated? We use the very simple formula under low strain condition. But if you know the shear wave velocity, if you know the density of the medium, then you can find out Gmax. Okay, so Gmax is rho Vs square. So once you know the shear wave velocity, you can easily get a plot of shear wave, shear stiffness versus the depth. Now there are various types of MSW survey. The first category is called as active MSW, where we use a hammer to strike the ground surface. So we have a hammer, we have the series of geophone which is kept in a linear array, and in this type of survey the hammer striker and the geophones all are kept in a collinear form. However, this gives in general a lesser depth of investigation, and we resort to other techniques. If we are not using a hammer, then what we have is called a passive MSW. So we have two different categories: passive remote MSW and passive roadside MSW. Here we are using the ambient vibrations. As the name suggests, in roadside we will use traffic vibrations and use the same linear receiver array kept parallel to the road with an offset, and we use the traffic vibrations for getting the signals through the geophone. In passive remote, it is a bit different. Apart from traffic, whatever ambient vibration is there, micro tremor, wind, machine vibrations, sometimes tidal wave vibrations, all those we collect. In this case, we keep the geophone array in a 2D form. It may be a circular, square, cross wire, anything, so that it can record waves coming from different directions. In today's talk, we will concentrate on active MSW and not on the others. Although by principle, the analysis and all the things are more or less the same. First, let us look at the MSW survey components. We have the hammer, we have the plate, we have the geophones, which looks like somewhat whatever is shown in this figure. It may be an electromagnetic one, it may be an electrokinetic one, it may be a piezoelectric one. So whatever is within this cascade, that governs how or what way this geophone will function. Target is the same. We find out the micro vibrations in the soil through this geophone. So what we do, we lay down the geophone in one particular array with some particular spacing and an offset. Offset here refers to the distance of the hammer plate from the first geophone. We can place it on the ground, or we can even place it on the hard paved surfaces, but here we have to use some tracer blocks so that they get proper contact with the ground. This is the data acquisition system which we use. So all these geophones with these yellow colored cables get connected to this. So this data acquisition system is responsible for recording the data from the field. So one such example is here where the data recording is going on. In the MSW procedure, so there are three basic steps: data collection, dispersion analysis, and inversion analysis. Data collection, as said, we do it in the field. Let us say we have a field with some soil layers. We place the striker plate, we give a hammer strike, and as soon as we give the hammer strike, a bunch or packet of waves get generated. Waves of different frequency, wave of different wavelength. So they get generated, they start passing through different soil layers, and they get collected in the geophone receivers kept on the linear array. This entire principle, or this entire phenomenon, works on the principle of dispersion. What is dispersion? Dispersion states that waves of different frequency travel with different velocity through the heterogeneous medium. So once you are giving the hammer strike, waves of different frequency will be generated and they will travel with different velocities. Now, if we can identify each of these waves of different frequency, and if we can identify for each of these waves of different frequency the particular phase velocity or the propagation velocity, what we get is basically a plot between phase velocity or the propagation velocity versus the frequency. Let us say we identified each of these waves, we found out their combination of frequency and phase velocity, then the plot what we get is called as the dispersion curve. So based on the principle of dispersion, we can find out this particular dispersion curve. How does it help? This dispersion curve is then passed through a series of procedures, which is then used to finally give us the shear wave velocity profile with the depth. So as stated, we have three basic steps: data collection. We have a series of procedure to find out the dispersion curve, which is called dispersion analysis. We have a series of procedure to find out the shear wave velocity profile through the inversion analysis. So we'll just discussing very briefly. So in the dispersion analysis, the basic fundamental is very simple. All of us have read in our UG level itself. It relies on Fourier transformation. So what does Fourier transformation say? If we have any time dependent random phenomenon, let us say in this case a random wave, through Fourier transformation we can convert that random wave into a bunch of sinusoidal wave, right, through sine parameter which is given here. So that bunch of sinusoidal wave, each of them will have different frequency, different phase velocity, and different amplitude. So what we see is something like this. We have the random wave. This is time. This is amplitude. In the time domain, we can see the random wave. Once we apply the Fourier transformation, we will get a bunch of sinusoidal wave of different frequency and different amplitudes. So this direction, we see the Fourier amplitude. So in the longitudinal direction, whatever we plot is the frequency domain result. So we have the frequencies of each of these waves and what amplitude does they carry. This is exactly the way how these MSW signals are analyzed. So first we have the time domain record which you collect from the field. On this left hand side you can see a typical MSW record from the field. The vertical axis is time. You can see many branches here. So each of the branch represents the geophone record. So there are 24 number of geophones in total. Here offset refers to the distance of any particular geophone from the initial point of the strike. And then you can see all these undulations which show that there are a bunch of waves which is passing through all this geophone. You can understand or at least visually recognize different energy level, different frequency, all of them intermingling with each other. Once we do Fourier analysis over this one, what we get is basically the frequency domain understanding. We get the frequency versus phase velocity. Each of these points we identified as each of these sinusoidal wave with a particular frequency having a particular phase velocity. So what you get here is basically your dispersion curve. So this I am telling in a nutshell, but there are complicated processes involved in this. So the target of dispersion analysis is to get this dispersion curve from the data acquired from the field. The next step is inversion. Now, as the name suggests, we have to invert something. So let us see what is forward modeling and what is inversion. 1 plus 2 equal to 3. Whatever you do, 1 plus 2 remains equal to 3. However, in inversion, if we start from the right hand side, 3 equal to, it may not end up in 2 plus 1, right? So we may have unique inversion, we may have non-unique inversion. Let us say, we say x1 plus x2 equal to 3 and x1 is equal to 2 is only possible when x2 is equal to 1. So if we write 3 equal to 1 plus x1, so x1 has to be 2. So this is a unique inversion. However, if we write x1 plus x2 equal to 3 and we modify this equation as 3 equal to x1 plus x2 and we say x1 and x2 can take any real values, so there can be innumerable combinations of x1 and x2 leading to 3. That means there is no single answer. So that's why this is a non-unique inversion and all real problems, including what we are discussing, have non-unique solutions. Many combinations of the input can lead to the same output. You can take different roads to reach your office from your home. Your output remains the same, but your paths change. So the problem which we are talking about here is to find out the shear wave velocity profile from the dispersion curve. Actually, this dispersion curve is the result and shear wave velocity profile is the cause. So if you know the shear wave velocity profile, actually you can find out a particular dispersion curve. Rather, the reverse is very difficult. So here we move from result to cause. And here, when we move to the cause comprises of many parameters. First of all, the total depth. Then how many stratification will be there? What will be the thickness of each stratification? What will be the shear wave velocity of each stratification? All these are unknown to us and you need to find. So it's not really very easy. There we take help of inverse optimization problem. Believe me, inverse optimization is not really very simple. It has its own inherent complications, but the concept is very simple. So I will show you how we use this in this present analysis. So what we do is that instead of going inverse, we start through a forward modeling. We assume a shear wave velocity profile first, what we call as the initial earth or VS model. Using the initial earth or VS model, there are very well established mathematical formulations to obtain theoretical dispersion curve. One example is given here by Schwab and Knopf. Using this particular formulation, we can find out the theoretical dispersion curve. You already have your experimental dispersion curve from the field. You try to match between them. One can say, how we will start at all? We don't know anything about the initial model from where we start this analysis. Today, the computational capacity or computational efficiency has gone up to such a beautiful level. Today, there are many ways where these problems do not depend actually upon the initial model. So you can start blindly, anything and everything, whatever comes in your mind. What happens is that if you start with a very bizarre initial model, then the convergence takes time with the final intended result. So it is always preferable that you start with a conducive initial model. If you don't have, it's fine. But in the project site or its nearby area, if you have any borehole record, you can have SPT values in that borehole record, and using that SPT value, you can start with the initial model. So through this expression is a very standard expression by Imai and Tonochi, where you convert the SPT n value to the VS value. N is the SPT and VS is the value which you get. So you have the SPT n profile. From that, you get the VS profile for your initial model. So as stated, you use the initial model through theoretical dispersion curve to find out this theoretical dispersion curve and compare it with the measured or experimental dispersion curve. And definitely it's not going to match. What you need to do is to find out the difference or deviation between these two, which is basically here stated as error. Here I have shown with RMSE, root mean square error. You can use any statistical counterpart for that, whichever you feel fit and whichever you feel better. What we do, once we find this error, then there are techniques of model updating through error backpropagation. So we use this error to change the VS model from the one which we have considered initially. So we use a new VS model, again run the same procedure, check the RMSE error. If it is reducing, we again look to the error and backpropagate it to do the model updation. We continue this process, it is an iterative one, and we stop at some point where we feel that the RMSE error has fallen down below some threshold. Whatever is the VS model obtained at that point is considered as the final, or we say the most probable substrata model which is possible from this test. This ends the fundamental theories. Lot of other things are there. Now I will show how we used these understanding to an actual project which was a very prestigious project carried by us. So we did an MASW survey at a Geophysical River bridge site. This is a tributary of River Brahmaputra. A 4-lane bridge is coming up, 1.2 kilometer long, and this connects two highways, NH52A and NH37 in the Tejpur district. The intention, so this is the Google map of the bridge. You can see the bridge is located here. Geophysical flows beneath that and meets Brahmaputra. Now, Geophysical River, or this part of Brahmaputra River, is actually very braided. It carries lot of debris, lot of soil particles, lot of fine particles as well. So this bridge is intended to connect these two regions, Dolabari and Jamugurihat, so which in absence of this connection takes another 40 to 50 kilometers through all the way on the other side. So this bridge is a earmarking bridge in this region. So NHIDCL took up this project and they developed the plan proposal for the bridge, 2 abutments on each side, one here, and the bridge will be made up of 24 piers passing over the river, Geophysical. Issue is that they have planned for the piers or the well foundation. They started going to that area, started drilling to get the idea of the soil profile, but they found that in certain part they can drill only up to a very low depth, then get penetrated into the rocks, whereas in some other pier location they can easily go up to 35-40 meter depth and can still not get any hard bed. So they approached us to request that if we can devise some way to find out the substrata profile. So we helped them with the MASW at the riverbed itself. So we went in the dry season. You can see this is the riverbed. It was extremely sunny, extremely hot, temperature soaring up to around 42, 43 degrees in the bed because the sand was giving all the radiative components. And then we did this test on the riverbed site for 3 days. So we went through this entire stretch. We did active MASW survey, but on a roll along mode. We tested at each pier location, at each intermediate part of the pier location as well. So we did it on the very dry sand. We did it on some of the part where wet sand was available on some island. And with all these efforts, we could finally complete the test in 3 days. We started working with the analysis part. So what we get first, as already mentioned, we get raw data from the field. Now, since this site is unknown, we don't have any borehole record, so we cannot take help of any other available data which is a priori involved. Okay, so in this particular case, we collected the raw record. Now, this raw record, along with the MASW signal along with the energy signal, contains many noises. We have to do some pre-processing with the record. We clean up the record through processes called filtering and muting. I will not go into the details of that. You can see all of them in our published papers. We get a cleaner record, filtered and muted data, but you can see there are many waves of different amplitudes and different velocities involved. So using this filtered data, we find out the dispersion image from a single record, one particular record. But what we noticed in the field is that what we do in theory, that one dispersion image from a single record is enough, in the field it might not be so, depending upon your soil characteristic itself. So here what we applied is called dispersion image stacking to enhance the resolution. The stacking, you can think of repeating the experiment and superposing the dispersion images of repeated experiments over one another. So we repeated the experiment at the same place, same configuration. We repeated 4 or 5 times, and then we superposed 4 stacks to get a much better dispersion image with a much enhanced resolution. Once you get this dispersion image, your next step is dispersion analysis. Now, over the period, we developed a new technique of automated extraction of dispersion curve. So that you can again see in my research paper from the group. I'm not discussing that, but what we get is the dispersion curve, phase velocity versus frequency, fundamental mode, higher mode. So all these multimodal curves are obtained. Once that is obtained, for each point, we use the inversion analysis and found out the shear wave velocity profile. But this is only for one location. You remember we did the roll along survey. We tested at each peer location. We tested at each intermediate location between the peers. And then we clubbed the shear wave velocity profile obtained at various locations to develop the 2D profile. So that's where we get this particular final representation of the subsurface of the Geophysical riverbed. It's a beautiful, beautiful outcome which we have obtained with so many inherent understandings. You can see this color bar which shows the shear wave velocity. The deeper the color towards the red, so blue, green, yellow, red, the deeper the color towards the red, higher is the shear wave velocity, indicating higher is the stiffness of the material. In the top 7 to 8 meter, it is very shady in color. It is of very low shear wave velocity. This represents the erodible top sediment, and this determines the scour depth of that particular riverbed. Then you have this patch which is of bit higher shear wave velocity, around 420, 430. Then you again have this blue patch which is of lower shear wave velocity, which represents a soft sediment layer, probably the fine soft sediment carried by the river. Now, as I told, this river is very braided. It carries a lot of debris in different cycles of its flow. You can see in between these soft sediments, there are very hard or sparched hard layer, which may be some boulder deposits, some rock deposit, some hard gravel type of deposits, which have eroded from the hill slopes and brought to this point and deposited during its lean period. As you go deeper, you find more and more higher stiffness material, and this material has a stiffness of around 1500, which we can well consider as the fragmented bedrock. So the interesting thing, what we found out is that what we were called for, the project management party told that at some point, specifically around Tier 12 location, they could not drill beyond 15 to 16 meter. And we exactly found that there is a parched hard layer through which this particular borehole would not have gone through their drilling techniques. We also mentioned at some other location, they could drill well to higher depths around 35-40 meter without any problem. And that's absolutely fine. Around Tier P19 where they were doing the drilling, you can see this soft patch and there is no intermediate hard patch in that form. So they could easily drill up to this level. So we could easily validate what they have observed during the drilling. Another very important feature. So in these active MSW, in general, you will not find records beyond 25 to 30 meter, records of not high resolution. But many innovations which we have done during this process in our theory, and when we applied this in our practical project, we really did a marvel. For the first time with active MSW, with automated extraction, with dispersion stacking, we could go up to a depth of 130 meter from the surface and find out the substrata characteristic with exposing or exhibiting the bedrock level as well. And we are very proud to say that this is the longest single stretch of MSW survey done in India until date. And I really thank the students who carried forward this work in that hot and very difficult condition, but finally came up with inexplicable result. So in that way, we got a very good publication as well. You can look for further details in that. Now, MSW survey, as we were discussing, gives you the shear wave velocity profile, but we should be in a position to use the shear wave velocity profile for much better things. So we can use the shear wave velocity profile for ground response analysis and liquefaction studies as well, which we will discuss in this particular module. So in ground response analysis, what we find, as the name suggests, if there is some earthquake happening or originating from its point of origin, the waves travel from that point and reaches the ground surface through various strata. Depending upon the characteristics of the strata, depending upon the shear wave velocity profile of the strata, the wave which reaches from the point of fault rupture to the surface may get amplified, may get attenuated or dampened, and we try to find out what is the response of the ground due to the propagation of this wave. So that forms the crux of ground response analysis. Why is it important? Because ultimately when it reaches the ground surface, depending upon the intensity what is experienced on the ground, your structures start responding. They respond differently in a minor shaking and differently in a strong shaking. So to identify the response of the soil to response of the overlying structure, so we find out this ground response analysis, and through these studies we try to find out how the soil will behave. So it is the response of soil substrata. The assumption is that the layers are laterally homogeneous, so basically it is a horizontally layered deposit and it is subjected to vertically propagating shear waves. What are the fundamentals necessary for that? We need to know a bit of wave propagation, wave mechanics, strong motion characterization, the characteristic properties of the strong ground input motion, and the dynamic characterization of the soil, its dynamic properties and liquefaction parameters. I'll just briefly tell them, not going into much detail. Before going to that, we should mention here that several types of ground response analysis can be done. It can be a linear, equivalent linear, or non-linear one. It depends upon how much strain is induced, whether the earthquake motion is of low intensity or of very high intensity. Whether you carry out a time domain or frequency domain analysis, it depends upon what mode of analysis you choose. Total stress or effective stress, it depends upon whether you are considering the pore pressure or not, whether water table is present or not, or whether there is any chance of generation of pore pressure or not. Depending on that, you choose between total and effective stress. Meshing and non-meshing analysis, this depends upon the type of loading, unloading and reloading rules. So this is a part of a greater theory and this controls how the soil will behave. I'm not going into the detail. You can again do it in 1D, 2D or 3D format depending upon your problem and the rigorosity of the problem. The most general is non-linear, time domain, effective stress, non-meshing, 3D GR. However, computation cost will also be very high in that particular case, and depending upon the project which you are handling, depending upon the requirement of the project you have, you may actually reduce this general problem statement to many simplified problem statements. There is a very beautiful software called Deep Soil, which is freely downloadable from this website. You need to register and download it, which is a fantastic software for carrying out 1D ground response analysis. So in 1D means it considers a soil column and find out the response of waves propagating from the bottom to the top. The beauty of this software is that it encompasses many models of pore water pressure generation and dissipation. Now, when you do a ground response analysis, if water is involved, you need to have, or you must have, a very good pore water pressure generation and dissipation model. This software gives you very good opportunity in that. It's a very beautiful software. One can always download and practice. What are the requirements of the ground response analysis? So you need to first of all know the shear wave velocity profile of the substrata. We already discussed. You can do it through 1D MASW. You can do it through roll along 2D MASW and then take sections at various places. You can even find out from the SPT n value profile. Again, this equation will help you to convert SPT n value to the VS profile. You can do some cross-hole test as well to find out the VS and VP profiles. So whatever you do, you need to have the shear wave velocity profile of the substrate. Next, you need to know the strong motion input characteristic, their amplitude, their frequency, and their duration. These are important because these governs how the soil will respond. Here I am showing two motions, one of Kobe and one of Sikkim, these two motions you can visually recognize that they are largely different in their time duration, they're largely different in their intensity and amplitude, as well as from this particular plot we cannot comment on frequency, but when we see a Fourier transformation of that, a Fourier spectra, we can see they're largely different in terms of their frequency bandwidth and the energy carried as well. So you need to have all the information about the strong motion. These are only few informations which are passed here. All the rest of informations are given in this particular table. You can use the software Seismosignal or any other similar software to find out all the strong motion input parameters, and these will help you in further analysis. And you need to know the dynamic soil properties. So we have our monotonic soil properties from our general lab test, but we need to carry out dynamic soil properties because here we are referring to strong motion where huge strains can generate. So strain dependent properties are immensely important. We find out shear modulus degradation curve, we find out strain dependent damping ratio, we find out liquefaction parameters. You can carry out cyclic triaxial or cyclic simple shear test. I'm showing one apparatus of cyclic triaxial apparatus which we have in our lab. So it is just like a triaxial apparatus which we use regularly with these additional features of giving cyclic loading either as stress or strain. And there is a base pedestal again which can move up and down. Apart from whatever we have in a general triaxial system with all the measurement points through LVDT and the valves and the transducers, this equipment which we have also has a very beautiful additional feature where we can mount transducer or these measurement units on the sample at its midpoint itself, so that we can find out what happens in the soil sample during the test, not from the outside but real time inside whatever is occurring in the sample in terms of deformations. So we find out the shear modulus degradation and strain dependent damping ratio. I'll not go into the details of this. So once we carry out some strain control test, so this is a special test, as the name suggests, strain is controlled. So your input is strain, your axial strain is a sinusoidal curve whose amplitude remains constant with time. Based on this input given, you find out excess pore pressure which gradually builds up with time in the saturated soil sample. As the pore water pressure builds up, your deviatoric stress or effective deviatoric stress goes down. So that means the soil sample is softening up. And when we plot the deviator stress versus axial strain, so what we get is basically the hysteresis loop. So this hysteresis loop is actually used in a series of process to find out the shear modulus degradation, how the shear modulus reduces with each cycle of loading and unloading, and we find out strain dependent damping ratio, how the damping ratio changes with each cycle of loading and unloading. We can also conduct stress control test. Again, the name suggests that we will give stress as an input and that will remain constant with time. So in this picture, we give deviatoric stress as input. That remains constant with time. What we measure is this blue colored line, that is the pore water pressure ratio, how it increases with the number of cycles. And this black colored line shows here the accumulation of the shear strain, how shear strain gets accumulated over the number of cycles. And again, in this case, if we plot the shear stress versus the shear strain, we get the hysteresis loop. Again, this hysteresis loop can be used to find out the degradation and strain dependent damping ratio. So what we get as the final output is this particular degradation curves. So these curves which are reducing down, these black colored lines, are the shear modulus degradation curve, which shear modulus degradation is G by G max. G max, you remember what we have found out from the MSW test, and G is basically at each cycle what is the shear stiffness. So this ratio constantly degrades. Two curves are here, one for BS, Brahmaputra sand, cohesionless soil, one for RS, that is the red soil or the cohesive silty soil, which we normally have in this region. Similarly, we have the strain dependent damping ratio, how the damping ratio changes with the strain. So if there are chances of high strain, what damping ratio we should consider. So these two parameters help us define the ground response analysis. Along with that, we also find out the liquefaction potential parameters, whether or not a soil is able to or susceptible to liquefy or not. Here we find out plots for excess pore water pressure ratio versus number of cycle governed by different parameters: CSR, cyclic stress ratio; DR, relative density; sigma C prime, effective confining stress; F, frequency of loading. Depending upon all these parameters, the same soil sample can actually generate different levels of liquefaction. You can see that when the excess pore water pressure ratio reaches 1, then the soil sample has got its liquefaction initiated. So for some CSR, it will not liquefy. For some confining stress, it will not liquefy. For some frequency, it will not liquefy. So we need to find out the combination of the CSR, relative density, frequency of loading, all of this together to find out the liquefaction susceptibility of a soil. So we carried out this extensive test in our lab for Brahmaputra sand, for the cohesionless sand ample in this region, and we could very well develop a liquefaction criteria specific for this particular regional sand. And this again got published and actually got quite a few accolades. So now all these together, we need to do the ground response analysis. So I will show you a case study, what we did for Guwahati city as well as for IIT Guwahati. So in Guwahati city, so you can see this part of the region where we collected soil samples, borehole records from innumerable number of sites and boreholes. Around 670 borehole records were collected. Then we took up IIT Guwahati, since it is within the campus. Again, we have many borehole records within the IIT Guwahati, and for this particular campus region also we did the exercise. So this is one typical borehole profile of a record from Guwahati city somewhere, and you have these SPT values. From that SPT value, again using the same expression which we were mentioning earlier, you can find out the shear wave velocity profile. You can use the strong motions. Two of them I showed here. Deep soil contains innumerable number of strong motion. You can add to that, and you use the dynamic soil properties. We used the dynamic soil properties which is specific to this region. Deep soil gives you some standard properties as well. Once you incorporate all these in ground response analysis, you get some specific outcomes. So we use deep soil. You get to know the hysteresis loop, whether it behaves in a linear manner for the lower intensity motions, how much nonlinearity is generated in the hysteresis loop. You get the PGA profile. So it is the peak acceleration, peak horizontal acceleration with depth. The bottommost point is the peak bedrock acceleration, which you have used as input. So from this profile, you can find out whether certain layers are amplifying the signal when the wave is propagating from bottom to top, or whether certain layers are de-amplifying the signal when the wave propagation is taking place. Then at the ground surface, we call it as a peak ground acceleration or PGA, whether the full amplification or full de-amplification, or how much is the extent of amplification and de-amplification is obtained due to the various earthquake motions, due to the various borehole soil profiles. All those can be found out. We can get spectral acceleration. How does it help? So once you get the spectral acceleration, you use these data to design or analyze your overlying structures. You can get the maximum strain profile. How does it help? Again, if some layers are showing very high strains, so that gives an indicator that there is high mobility in the layer. There might be chance of softening in the layer, which can be initiated by a liquefaction phenomenon. So this gives an indication of liquefaction or cyclic mobility. You can find out the liquefaction susceptibility through maximum shear stress ratio. So tau by overburden pressure. So anything of this ratio greater than 1 is an indicator of liquefaction. So remember, it is indicator. It does not confer that it has liquefied. It is an indicator of liquefaction. Anything below than less than 1 keeps it safe. And finally, if you feel that some layer has high strain, some layer has high shear stress ratio, analyze the hysteresis loop for that layer. And if you see such hysteresis loop where there are two loops with different strain levels for the same layer, then it indicates chance of liquefaction or cyclic mobility. Now, we did this exercise for all the boreholes of Guwahati city, including IIT Guwahati, and then we found out the PGA value of the entire city. And this we did, this particular figure shows an example where we used the peak bedrock acceleration of Nepal earthquake, which was 0.18 G. That means at the ground surface, if you find anything greater than 0.18, that means that particular location is amplifying the motion, which is more catastrophic. And if at any point you find out something below 0.18, so that means it is attenuating, those regions are safer. We do not stop at PGA, we find out amplification factor, simply putting PGA by PBRA. So you get the amplification factor, similar diagram with a different representation. This tells you which site amplifies to what extent and what level of precautionary measure you should have. Then the issue is that in this previous figure, we had IIT Guwahati here, point number 3. It shows that it is somewhat in the level where things are not amplified. But sometimes with this big regional picture, the correct knowledge of local site amplification does not come into existence. So you need to carry out the local site amplification. Question remains how much local. So within a particular premise as IIT Guwahati, that can be considered as local enough, and then again some adjacent places can be taken separately. So we did the same exercise for IIT Guwahati with Sikkim earthquake. This particular figure is for Sikkim earthquake, PBRA 0.36 G. We found out the PGA values. Anything greater than 0.36 is going to amplify, anything less than 0.36 is okay. Now you can see there are written C-type quarters, B-type quarters, guest house. So these are a bit more vulnerable region in the campus if there is a huge earthquake coming into picture. Similarly, again PGA by PBRA, we found out the amplification factor, same diagram with a different representation. Now this peak bedrock acceleration, what we were using for Sikkim, Nepal, now this also has effect on liquefaction susceptibility. Susceptibility means you try to say whether the soil will liquefy or how much it will liquefy. It is a common notion that deeper layers does not liquefy, but no, it is incorrect. A good amount of seismic shock can liquefy quite deeper layers as well. So when we carried out this exercise with PBRA 0.02 G, very low level of shaking, we can find that at 1 meter, 5 meter, 10 meter, or 20 meter at different levels within the IIT Guwahati campus, factor of safety remains above 1. There is no liquefaction. When we carried the same exercise with a scaled up motion, 0.36 G, now we started to see substantial liquefaction susceptibility chances wherever factor of safety goes below 1. Not only at the shallower level, but at the deeper level as well. 0.36 G is a huge earthquake motion. So if such earthquake motion, which is not so uncommon in this region, probable, so for those cases, we need to think beforehand for the regions which we identified. Apart from FOS, we find out liquefaction potential index. Similar, but it is bit better. Why LPI is better? To understand that, we will look into this particular curve once more. Number of cycle in x-axis and excess pore water pressure ratio. You can see two small crosses here. So those indicate that for the first time in this particular number of cycle, the pore water pressure ratio reached 1. That means it indicates the initiation of liquefaction. It doesn't mean that there may be severe liquefaction. It depends how much will be the severity of liquefaction, depends upon whether for the substantial number of succeeding cycles, the pore water pressure ratio remains 1 or not. So LPI gives the severity. LPI less than 5 suggests no liquefaction. 5 to 15 suggests moderate liquefaction. LPI greater than 15 gives the severe liquefaction. So you can reclassify your area depending upon these severity of liquefaction. We did the same for Sikkim strong motion under various scaled motions, 0.02G, 0.06G, 0.18 and 0.36G, and we could find out different liquefaction potential index of the same place under different earthquake motions. So this gives us an overall picture of the ground response analysis and liquefaction evaluation which we can carry out. I'd like to thank my students again, Shiv, Devdeep, Madhulata, Pankaj, and many others who have worked very hard for all these understandings. For the next module, we will remain at Guwahati city, okay, but then we will go into rainfall. So we will talk a little bit about rainfall induced landslides and hazard zonation. What is landslide? It's very simple. Anything which is moving down, hurling down is a landslide. It may be a terrain landslide. It may be a subterranean landslide at the foothill. It may be a submarine landslide. It may be a rockfall. It may be a mudslide. So depending upon various characteristics, landslides are classified. One of the important way of classifying is how does the phenomenon occur, whether by rotation, whether by translation, whether by rockfall, debris. So based on that, we have many different categories of landslide. Apart from that, we have velocity as well as one of the category. We try to see how much speed with which the landslide is occurring. If it is very slow, you have enough time to protect it. If it is very rapid in the velocity class 7, it is a complete disaster. When we talk of landslide, we should understand what are causes and triggers. By nature, our slopes are stable. That is the beauty of nature. So there remains many causal factors which makes a stable slope marginally stable, and there remains triggering factors which lead to the eventual failure. Causal factors, any factor which makes the slope vulnerable and lead to its instability. It will not actually fail the slope. Several causes of landslide are there. Causal factors may be natural, they may be anthropogenic, geological, morphological, hydrological. You can see a plethora of causal factors here. Triggers are that event which finally leads to the landslide. In general, we category 3 different triggers: rainfall, seismicity, and toe excavation. We will talk only about the rainfall in this particular aspect. How do we do landslide analysis? All of you are aware of. If you have done slope stability analysis, you actually have done landslide analysis. Things become a bit advanced in that. That's all. Two approaches are there. One is local scale, one is regional scale. All of you have done local scale analysis where you consider a single slope, single landslide. You carry out the stability analysis by some limit equilibrium or continuum based method. In regional scale, we look into greater spatial extent. So in local scale, if I say I will do the analysis of one hill slope of IIT Guwahati, in regional scale, I will say I will do the entire landslide analysis of the entire Guwahati city. However, local scale only paves the way to regional scale. Without knowing local scale analysis, we cannot go to regional scale analysis. So in local scale, we find the stability. In regional scale, we find susceptibility. How much chance of landslide is there? That's what we try to find in regional scale, which is a bit different from the local scale. If we just recapitulate local scale landslide analysis, there are various methods. Limit equilibrium. In limit equilibrium, you all have studied infinite slope model, friction circle method, and a bunch of method of slices. However, the bit disadvantage in this is that it is only a force-based or equilibrium-based method, force and moment equilibrium. It will not give you the idea of deformations. For that, we resort to stress deformation analysis. We do all sorts of finite element, finite difference methods. And in this, the advantage is that not only you find out the slip circle, rather not circle, we find out the slip band or the strain localization band through which the mobilization takes place. In limit equilibrium, we had only one circle. Here we have a band. In this method, you can find out the evolution of the band. So how does the thing start from beginning and how does it end in slipping? Not only that, you can find out the deformation which is associated with that. So this can be done for soil slopes. This can be done for rock slopes where joints and other effects come into picture. So this is a picture from the jointed slope analysis. And apart from this method, we have method of wedges and discontinuum methods, which are more applicable to rock slope because there are tendency of rock materials or rock boulders to dislodge themselves from the parent material, and that gives a new dimension to the analysis. Many softwares are available. I have listed a few of them here: Plaxis, GeoStudio, FLAC, Rock Science. So all these can be used for local scale. We will talk about rainfall. Now, when rainfall happens, all these analysis takes a new dimension. Why? Because this rainfall leads to water infiltration in the slope. So there is a gradual degradation of the strength. So it is not like our simple slope stability analysis, what we carry out in our numerical exercises. So for this rainfall induced landslide hazard of Guwahati city, the project which we had taken up, so we need to first characterize the hill slope soils. Without characterization, we cannot proceed. So this is a map of the Guwahati city hill slopes. It consists of 8 major hill series. Whatever red you are seeing are the hills. So this is a digital elevation map. So the higher is the color or the deeper is the color, so the higher elevation it is. We went to various sites. We did investigation in the field for the geology, for the height of excavations, for the in situ densities, for the in situ permeabilities. We collected various soil samples to find out its constituent behavior, the particle size distributions, the consistency limits, all these things we did. In the rainfall induced, since as I mentioned that water will ingress through and slowly the saturation will take place, unsaturated soil mechanics has a big role to play. So not only saturated permeability, what we commonly find out through the constant head or the falling head permeability test, we need to find out the soil water characteristic curve, which is a plot of volumetric water content versus matrix suction. Least the matrix suction 0 is the fully saturated condition. So it shows that with the amount of moisture present in the soil, your hydraulic conductivity and water content will actually change. And that is very important for this rainfall induced analysis. Further, we did this test, the strength test, uncompressive strength test with various degrees of saturation. Why? Because all these excavated parts of the hill slope does not have the same saturation level. They fail at different degrees of saturation. To get the idea, we did with the different levels of moisture content how much of strength they show. And then finally, obviously, we did the direct shear test as well as the triaxial test to find out the inherent shear strength parameters. This slide, as mentioned earlier, without understanding local level, we cannot go into regional level. As simple as that. Then first stage, we take up local scale deterministic slope stability analysis. So deterministic analysis is the one which we carry out in the class in our normal exercise. However, that additional parameter we introduce, that is the rainfall. We took a representative hill slope in our region and subjected to different amounts of rainfall. This different amount of rainfall will lead to different amount of infiltration. So based on that infiltration, for two different soil, the left hand is for the red soil, the right hand is for the pale yellow soil, which is bit more cohesionless. We could see how the factor of safety of the slope changed with the time as the infiltration increased. However, if you see for the red soil, which is more cohesive, the factor of safety did not go below 1. Because in this particular case, the unsaturated characteristics is strong enough to have reduced permeability. However, since pale yellow soil, this figure on the right hand side is more cohesionless, more free draining, more infiltration takes place, factor of safety drops below 1 under different cases and leads to failure. So hydraulic conductivity curve is of immense importance in rainfall induced analysis. And again, based on that, we find out how the slope fails, what is the slip circle. The red patch gives you the safety probability. And if you see, this is 0.927. So this is basically the slope, the factor of safety indicating the slope had failed. This is deterministic. All the parameters are known. What happens when the parameters are unknown, especially soil parameter? In the deterministic analysis, for this entire slope, we consider one particular value of C and phi. In real case, you will never have one particular value of C and phi in a hill slope. Rather, you will have a distribution of C and phi. So for that, we conduct local scale probabilistic analysis where we apply random field. Not going into the intricacy, random field is basically to generate different C-phi combinations in the same slope and then analyze the picture. So we cater the uncertainty in the soil parameter. When we say a soil parameter has C of 10 kPa, it really does not mean that it has 10 kPa. Rather, its mean value is 10 kPa with certain standard deviation. Similarly, for friction, if we say it is 30 degree, it is not really 30 degree absolute value, it's 30 degree mean value with some standard deviation. So based on, again, numerous tests, we could find out the distributions, what is applicable to our particular region. And we found out these probabilistic distributions for C and phi. Then you also need to understand that C and phi will not increase together, rather they are inversely correlated. So you need to find out cross correlation between C and phi. In general, higher C leads to lesser phi. That is a natural phenomenon. So we found out again for our specific region the cross correlation between C and phi. Then another important point comes when in a hill slope you talk about change of parameters. Change of parameters does not happen randomly. So at one point, if the C is 10 kPa, just at the adjacent point, it cannot be 100 kPa all of a sudden. There is always a transition from 10 kPa to 100 kPa in some manner. This transition is delineated by correlation length. Within what length, how the parameters will change. We did that exercise for our region. So we found out various types of correlation length. So theta x and theta y are the correlation of parameter, in this particular case cohesion in x direction, cohesion in y direction. That means if my value of cohesion is C at one particular point, based on theta x and theta y equal to 15 meter, it will give me how C will vary from C to 2C or 3C in over this particular range. Same exercise we did for theta x equal to 15 and theta y equal to 5. That means in two directions the correlation are different, which is more like an anisotropic variation. Once you do this, your hill slope does not remain homogeneous as we normally see. Once we do that, let us say theta x and theta y both are 1, in this case both are 5, in this case both are 10, and in this case theta x is 10 and theta y equal to 2, that is anisotropic. Our now hill slope become or have random strength parameters. Depending upon this random strength parameter, depending upon this correlation coefficient, if it is small, the parameters are more random. If the correlation lengths are larger, parameters become to form pockets. If the correlation length is non-uniform, parameters form stratified deposits. And based on this correlation length, since it is probabilistic, now we no longer talk about factor of safety, we say probability of failure. How much chance for the slope is there to fail. With this knowledge, we move to regional scale stability analysis, where we do not talk of single slope failure. Now we talk of landslide susceptibility, what is the chance of landslide in a region, and landslide hazard zonation, which region or which part of region is going to fail. There are many softwares which are called physically based model, ShellStab, shallow stability, triggers for transient, SynMap for stability index mapping. All these softwares operate on digital elevation model in a GIS platform. So when you talk of region, you have to take care with the help of a GIS platform. So this is a representation which I have shown for Guwahati earlier. The raw DEM looks like this. So all these points are specified by their height and their location. So any 2 point, you can know the height difference and the distance. From this DEM, you calculate the different maps such as slope map, which is obtained directly from the DEM. You need to have the catchment area map to understand from where water is draining and where. You need to have idea of the steady state recharge map to understand the infiltration at different regions, and you need to have the idea of the groundwater table map where each region is demarcated by the varying groundwater table. With a series of analysis through the physically based model, we use triggers and seam map, we finally come to the stability index map, where in this entire region we say whether the slope is stable, critical, or unstable. Now you can see that since we generally say FOS less than 1 is failed. However, in the case of regional landslide, we still do not say it failed, because generally we refer to the probabilistic safety and the probabilistic stability. Now, in the regional scale landslide hazard analysis, it is very important to introduce rainfall and soil depth. So what we have to do for the region, for our region, what we considered, we collected 100 years data of the mean of the rainfall and found out the mean monthly rainfall and its variation. Okay, so based on that, we found out the very important input for such analysis, which is called rainfall IDF curves, intensity, duration, frequency curve. So it governs how intense a rainfall which occur for how much duration with what return period. That depends upon your meteorological characteristics of the region. So for this region, we found out the intensity duration curve. As can be easily understood, any rainfall of higher duration has lower intensity, and any higher intensity rainfall has higher return period. So that means, which says that rainfalls of different intensity, rainfalls of different duration will induce regional instability at different times, different laps of the year. So what we do along with that, we find out the soil cover depth as well. It is very important, because steeper the slope, lesser is the soil cover, greater are the chances of the landslide. So this also has to be incorporated in the map. So what we did, we found out FOS map at dry state. You can see more or less all the region or the entire region is safe, which states that if the region is dry, the landslide stability will not occur. If we have a rainfall, a 48-hour rainfall incurred, so in this particular case, you can see many parts of the region are coming out to be red, and even some are black. So this indicates that after a 48-hour rainfall duration, many parts of the region are susceptible to landslide. So incorporation of rainfall is very important, and this shows that this entire region, what we are considering rainfall induced landslides, is one of the prime consideration. What is the influence of return period? Today a region may not slide. Next year with sequential monsoon it may slide. Following year with sequential monsoon, more regions may slide. So we did the analysis for various return periods. You can see with the 3-year return period, most of the region is basically factor of safety is high, so it is safer. With increase in 10-year return period, you can see this reddish portion starting to evolve. With the 100-year return period, most of these hill slopes are going to face catastrophic landslide if not proper protection is taken. We do not keep this as individual. Rather, when we combine all these return periods, what we get is landslide hazard map. So in the hazard map, from the hazard map, basically we identify which region is going to fail in how many number of years, and accordingly, depending upon those region which has the chances of failure in lesser time, you need to devise your mitigation measures for them first and sequentially take up the other. Again, along with this, you can always incorporate the uncertainty of the soil parameter, so the landslide hazard analysis becomes probabilistic. So we do this entire exercise for different values of soil parameter. For this C equal to 13.3 kp and phi 19 degree, this for another set of C and phi, this for another set, and similarly other. You can see for each different set of C and phi, the landsliding characteristic is different. That means there are particular combinations of for C and phi of the region where sliding will be more predominant. We need to identify those slopes and take immense care of them and devise proper mitigation measures. What we do is that again we club all these maps together to get what is called a probability of failure map of Guwahati city, and that we obtain that in this particular map what we tell that all slopes are failable. In probability, none of the slopes are stable. It is only which slope has higher probability of failure and which slope has lower probability of failure. Based on that, we devise our landslide protection measures. So I would like to express thanks to Chiranjeev here. I would like to express thanks to Chiranjeev. He is the PhD student who has done this entire work on these landslide, rainfall induced landslide hazard zonation for this entire Guwahati city. The last small topic we will take up is a very, very pertinent topic of soft ground improvement using preloading and prefabricated drain. How is it related to the earlier ones? So this also has the culprit of water. You have to eradicate water and make it stable, or rather water ingression leads to the destabilizations of soft grounds. So what are the fundamental principles required? You all have studied consolidation. Only thing is that you all have studied vertical consolidation. To this we need to add radial consolidation and radial drainage for excess pore water pressure dissipation. Just seeing the basics. So if you have a very soft ground of slow draining material, very low permeability, our target of the soft ground improvement is that the ground should be having good bearing capacity even before the actual construction. So for that we preload. So we try to see that the pore water pressure rise takes place even before the actual construction by this preload, which is considered as a fraction of actual load, and then we try to gain strength. But then what happens in this, that this preload which is given at the surface releases the water from the upper layers, keeping in mind that this is a slow draining material. Pore water pressure remain accumulated in the lower layers. They are not eradicated out. So our purpose is not that solved. What to do? Put pipes in that. Simply put some vertical pipes which we call as vertical drains. Now you have put these vertical drains, so they give you infinite permeability at specific instances or specific spacings, and now when you load, the soil or the pore water pressure which is generated at deeper layers is basically released through the pore water moving from the soil to these vertical drains and then getting eradicated from the surface. If we look into the vertical drain, prefabricated vertical drain, as the name suggests, this is a custom made. So we basically have a plastic core in between which acts as those straws which is put in your coffee in the airport. So you can bind these straws together and then you get a filter sleeve so that the soil does not migrate within and clog this material. So we have a filter jacket and a plastic core. That's what all is PVD, prefabricated vertical drain. How do you install? So it is a mechanized process of installation of prefabricated vertical drain in the ground. So once you install, the pore water pressure starts moving to these drains due to the hydraulic gradient. Then it starts coming up. Then there will be horizontal drains which will carry the water and it will be basically evacuated from the site. In order to accelerate the process, you give this preloading so that more load is given and more excess pore water pressure is drained out. These drains are put into particular spacing patterns. So you may have a square pattern, you may have a triangular pattern, you may have a hexagonal pattern, and depending upon each pattern, the influence zone of these drains change. And that controls the efficacy of the vertical drains in the field. This is a mechanical representation of a vertical drain. So the innermost pipe is the drain. The outer dotted line basically indicates the soil which gets disturbed when the drain is pushed into, which is called as the smear zone. So smearing takes place around this vertical drain when they are pushed into the ground, and the outer cylinder represents the influence zone. So in this particular case, if we see the radial direction cross section, so we can see the outermost radius as the outermost zone or the influence zone, and the inner radius comprises of the smear as well as the drain. So water flows from all direction in three-dimensional manner into this drain and gets ejaculated from that particular place. So as I was mentioning, the inner one is the drain. Then we have the smear zone, the soil which gets disturbed. Now when the soil gets disturbed, its permeability becomes lesser. So Ks is the permeability of the smear zone, and Ks is lesser than Kh, that is the permeability of the intact zone within the influence region. What we do for these cases is finite element modeling and analysis. You can do this entire model as a 2D plane strain condition or a full 3D, depending upon what type of embankment, what type of loading, and what you have in the longitudinal direction. In each of these cases, you should have a plan of preload, how you should give the preload in stages, and based on that, your analysis is governed. So this plan of preload is not really an input, rather an outcome of the analysis. So what are the outcomes? What do we see in these analysis? We see how does it deform, how does the drains bend, how does the settlement takes place over the time. So over the time, water is moving out, voids are basically getting closed, settlement is taking place. We see the shear stresses. So due to this settlement, which part is stressed more on the slope? If required, those parts has to be taken care with some precautionary measures. We try to see the pore water pressure before consolidation and pore water pressure after consolidation. So this gives us the idea how good the drains are behaving. So if you see, the maximum pore water pressure before consolidation in this region is 90 kPa, and the maximum pore water pressure after consolidation is 76 kPa, and only in this smaller region. So this indicates that the drains are behaving quite well. We always need to check how influential is the PVT by considering only preloading and preloading plus PVT. Again, what we are seeing here is the pore water pressure. You can see that the pore water pressure or the maximum pore water pressure occupies a much higher zone when only preloading is given, because there is no way to escape for them. Whereas for preloading plus PVD, since the drains are acting as escape material, these pore water pressures once generated the escape. So that means PVDs help in the reduction of the pore water pressure zone. So the zone is much higher when only preloading is there. The zone is immensely lower when preloading plus PVD is there. So we try to see the variation of excess pore water pressure with time. Blue colored is without PVD. You can see much higher excess pore water pressure is still remaining since they did not escape. Whereas with PVD, after the pore water pressure peak is generated, there is substantial reduction in the pore water pressure, and it is much lower than the other case without PVD. And since pore water pressure reduction is more in with PVD, the settlement is also more, and that's what is our target. Before the actual construction, the ground should settle to the maximum, and in that way the soil should gain strength. And in this process, we also do some analysis with the smear zone effect to see how much effect the driving of the PVT has disturbed the soil and how does it affect the settlement. So it is more or less the same, only by changing the parameters of Ks and Kh in some ratio. So we get these results. So higher Kh by Ks means more smear has taken place. So lesser will be the settlement because it will prevent the pore water from escaping through the drain. So it creates a lower permeability zone all around the drain. Again, I should thank here my two students Rajesh and Sai Kiran for doing this entire work. We did this entire work in theory, then a chance came that we apply it in practice, and it was a very, very prestigious project for us. So before going to that, I just mentioned that there are some influences about the depth or the spacing of the PVDs as well. The PVD can be given in uniform fine spacing, let us say 1 meter center to center. It can be in sparse spacing, let us say 2.5 meter center to center, and even in unequal spacing, lesser spacing in the center because more pore water pressure will be there, and sparse spacing at the edges. And accordingly we get different types of settlement features. Obviously, if you have the finest spacing, your settlement is higher, but your cost is also higher because enormous number of PVDs has to be installed. This is again governed by how much we require the pore water pressure to dissipate between the drains. So this is a sectional view. So these three blue lines, what we are seeing are the drains, and these intermediate contours are the pore water pressure distribution. So as you can see, at the point of the drain, the pore water pressure becomes 0 because it is draining out, and in between the drain it remains maximum. So how much spacing we will be giving at what location will be governed by how much pore water pressure can be tolerated in between the drains. Sometimes if the layer is too thick, we give floating PVDs. We cannot put the PVD to the end of the soft layer, and then based on what level of floating PVDs is given, at what length the PVD is terminated, different settlement characteristics come into picture, and then it has to be the decision of the engineer and the consultant that as per design requirement, what length of floating PVD we should adopt. As I was talking about the prestigious project, it is about the heritage railway station at Udaipur, Agartala, where a railway yard and the railway station is to be built. With the application of preloading and PVT, it was supposed to be built in a ditch marshland. There were no rail connections beyond Agartala, and this created a historical change in the communication in this part of Tripura at Udaipur. So this was the site. You can imagine what harsh this site can be. So it is a marshland and a ditch. So all around is the catchment area. Water always flows in, and somehow through this only the railway line has to be taken because of the communication distance and all those things. You can see the waterlogged areas. Embankment was started to be built, but then it was seen as the embankment is built, the soil is keeping on settling because it's a huge marshy ditch. So enormous amount of settlement was taking place, which was unacceptable. So what we did, we called or worked with the agencies, we worked with TechFab at this particular place, and then we devised a plan of PVD ground improvement in this particular area. You can see all these PVDs, as I was showing in the earlier picture, has been installed. A geosynthetic blanket and a sand drainage blanket is given, and then preloading is done. So this is the preloading going on. So based on these PVD installations, sand blanket and geosynthetic blanket, along with the preloading, the water escaped very quickly, and then we started doing the analysis. A very important learning came to us who work in theory from this practical project is the incorporation of strength gain in the analysis is very important. In general, in all these analyses, you take the strength parameter to be constant from your lab test. But what happens is that when you do the calculation without considering strength gain, you end up with certain preloading plan. So the height of embankment on the left hand side is the preloading plan. Corresponding, you have the degree of consolidation. So you can see that even up to 3 meter height, one storied building, so the consolidation is only going up to 63.16%. But when we were testing at the site, it was showing much higher consolidation feature, which is not coming out from this theoretical calculation. Then we started looking into the problem and came up with the issue that as you increase the load, in this case the preload, as the effective stress is increased within the soil, the volume compressibility and the permeability of the soft soil goes on reducing. That's very natural because the water will be ejected out, the soil particles will come closer, so it will be experiencing lesser volume change and it will show lesser permeability. And since it will be more packed, more consistent with the preloading and with the stages of preloading, there will be enormous amount of strength gain, which is very important to consider in the calculation. Now you can see when we consider the strength gain in the calculation, at 3-meter height of the embankment, the degree of consolidation has gone up to 87%, which is far fair enough. So this strength gain during consolidation should be considered in order to devise a more proper planned preload, which is immensely costly as well. So this proper consideration of strength gain helps to save unnecessary preloading requirement. So all this being done today, last year there has been the startage of the yard and the rail connection connecting many villages there, and today what it looks like. So this is the picture of the Udaipur station today with the station building. This is the yard where we have actually done the work, and this is the entire scenario. So all around is still marshy, let it be. So our PVTs are working fine, and till date there has been no report of any other malfunctioning or anomaly at this site. It was a very prestigious project for us. Talking of all this, I have bothered you enough through all these things, many issues, many advanced things. I'll give only 2 final remarks, not summarizing or anything. We talked for this entire duration about practice and theory and their blending. And I started with a picture where it showed practice and theory are like that angry couple or the crossroad signpost. So we should take into our mind, we should keep into notion that theory versus practice arm wrestling is not what is recommended. It is a big no-no for us. Theory and practice has to go side by side. They have to hold hands, and that would bring out more beautiful and more technical engineering aspects and solutions. So at the end, I would like to render some acknowledgement, definitely, first of all, to the organizers of the conference, where we actually got a platform to discuss some interesting issues, some of the things what we did. And it is not about what we did, rather what we did as a geotechnical community. To all my students who are basically the workforce, they work day and night to bring out these findings. To all my academic and industry partners, supporters of the brains, and most importantly, the funds, and all those researchers who laid the foundation of these present day discussions. We would not have discussed anything at all today without their age-old contribution, not forgetting the father and the grandfather of geotechnical engineering. So thank you all for your very patient hearing. I believe we paved some way for new research, new understanding, and this is just a dot. And there is enough field left for us to end up. So these are my links to the home pages and my ResearchGate profile, where all the research material, whatever I told today in the presentation, everything is available, freely downloadable. If you are not getting, you can always contact me. I can send you a copy and for further discussion. So that will be all from my side. Thank you, everybody. Thanks the organizers, anybody who is hearing or listening to this presentation. So that will be all from my side. I will hand over the session now back to the organizers. Thank you.
Big thank you, sir. Big thank you, sir. First of all, congratulations to you and your group for the longest stretch of SW survey of around 130 meters, and also some other wonderful works. I must mention our deep sense of appreciation for you for your wonderful explanation and presentation. You are really enlightened with your knowledge and presence, and especially if, as I'm also from geotechnical specializations, it's my pleasure that I have listened to your lecture from this close end. In fact, you'll be happy to know that our next session of webinar will be on the earthquake disaster management, but from a separate point of view, from a structural point of view.
Yes.
Yeah, it is our pleasure that you have spent a part of your valuable time with us. Thank you again, sir. Now, I
Thank you.
thank the wonderful participants who have turned up in such great numbers, not only from our institutions, rather also from various other institutions also. Thank you so much for your cooperation. Now, we will move to our next segment, a question and answer session. But before that, to all the participants, I just want to say one thing. The feedback form link is given in the description and which will get activated after the session is completed. You all are requested to submit your true feedback, preferably within 3 p.m. A certificate of participation will only be issued to those participants who will be filling the form, the feedback form. Okay, and about our next webinar session, the next webinar session is scheduled on 25th August. As I have told you, that the webinar will be on the earthquake disaster mitigation. For the details of the coming webinar, you can track our Facebook page, and it will get uploaded shortly. So now we will bring forward or put some questions asked by the participants. Dr. Shagata Desai, the mic is yours. I'm handing the mic to you. Please start our interactive session. Dr. Shagata Desai.
Yes, first of all, I would like to thank Arindam sir for this beautiful talk, which is very essential for our geotechnical engineer. So, first question I have got, like from Amit Jadhav, IIT Mandi, why phase velocity reduces and frequency increases?
Okay. So frequency, I'll answer to this question. So frequency is much related to the wavelength. Okay. So as your frequency increases, your wavelength actually decreases. Now, once the wavelength decreases, so the wave which is generating from the surface cannot penetrate deep enough into the soil. And now the soils in the uppermost layers, since they have lesser confining pressure, so lesser stiffness from all sides, so they will not act as rigid as the soils of deeper strata. So due to the lesser confining pressure, your phase velocity actually reduces in the upper layers.
Okay, thank you. Next question I would like to ask, like from Rajesh Seth, what is the effect of seasonal change in soil moisture depth?
Okay. This answer is not very straightforward. Okay, because apart from the seasonal change, what is more important in this infiltration or the penetration of the soil moisture into the medium is the permeability and the tortuosity or the void spaces inside the soil. If your permeability is high, let us say we are talking of more sandy soil, and we did this type of activity in our childhood, right? You make a heap of sand and pour some water, immediately it will start penetrating inside. Forget the childhood activity. Nowadays we are in lockdown, so we are doing even cooking jobs, right? So while we are basically washing the rice, right, while we are cleaning the rice with water, once you incline the bowl of rice after you have cleaned it, the water actually moves out very quickly. Now add in that rice some wheat and then see whether it moves out or not. It will not. So that means as your seasonal changes take place, so as your rainfall capacity or rainfall duration, intensity goes on changing, along with that, whatever is governed for the moisture penetration is the permeability. If the permeability is lesser, more and more time will be required even for a high intensity rainfall to introduce moisture at deeper levels. Okay, so these two parameters goes hand in hand in order to understand how far will the moisture level penetrate inside the soil.
Okay, thank you. Next question I would like to ask, like from King Jong, sir, all inverse problems are inherently ill-posed and multiple solutions can satisfy your extracted dispersion curve. Then, without a borehole or other prior information, how can we be sure about the accuracy of the inverse analysis?
Very nice question. I really appreciate this question because this is one question for which we have worked for around 7 years to come out with something. The issue is that the once you don't have a priori knowledge, okay, so you are blind. So you don't know how much depth you will be taking into consideration, how many stratification you will be considering in the initial model, what should be the velocities of those. However, this ill-posed problem, as rightly pointed out by Kim, that these are all initial model dependent. Now, this initial model dependency, this problem has been addressed for very critical problems from long time. Now, if you see these optimization problems, whatever we are dealing with, nowadays we don't deal with this classical optimization anymore, where the initial model is actually the biggest problem. We mainly deal with now population based problem or biogenetics based problem. So we deal with genetic algorithm, we deal with particle swarm optimization, we deal with gray wolf optimization. So all these type of techniques work on particular population, not on a single initial model. So by using these type of evolutionary algorithms, by these biomimetic algorithms, we can actually erase off the effect of these initial model problem over these inverse analysis techniques, and that has been done. If you see all these biogenetic or biomimetic based algorithm techniques, there are immense number of papers where this initial model problem is eradicated, and that's what we do nowadays.
Next question from Arup Kuho. If frequency content of the SEC input is unknown a priori, how do we design structural safety?
Sorry, can you repeat once more?
Yes, if frequency content of the SEC input is unknown in a priori, how do we design structural safety?
Okay, so here this question is very tricky and not a straightforward answer is there for that. See, in general, if you see, we measure all these acceleration related things at the surface. Okay, so we put the accelerometers in the surface, we put the measuring devices at the surface, and we get the time domain record. Now, what happens is that when you measure at the surface, you are basically getting the amplified or attenuated or modified record. So if you do the Fourier transformation, find out the Fourier spectra of that, you are not really getting the actual bedrock acceleration or actual in-depth acceleration, whatever has been there. Here, one issue which comes to our help, I should say help, not exactly overcoming the problem, is deconvolution. Now, by deconvolution, if you have already known the shear wave velocity profile of the soil by any means, say it's the same SW or cross soil or anything, and if you have measured the acceleration versus time at the surface, with the help of deconvolution, you can actually devise the synthetic earthquake, again an inverse problem, devise the synthetic earthquake which would have come at the base of the soil profile and have resulted in the superficial acceleration time history. Issue is that whenever we say deconvolution, it is mainly a linear transformation, and we understand when we are talking with strong motions, it is bound that it will not remain linear at different portions, especially on the upper layers. Nowadays, again, you will find that a good group of researchers is working on nonlinear deconvolution, and many good papers also has come out of that. So if you are using those techniques of nonlinear deconvolution, you can find out, I should not say exact, but the most probable earthquake which have occurred at the base. Again, devise a model, put your structure in that, and then use that same deconvoluted earthquake at the base and do your analysis. That will at least give you much more insight than to stay zero by with only superficial measurements. Apart from that, I would just like to add, if you see the Japanese earthquake society, who actually is the proponent of the knet and the kicknet, now they have actually put deep surface accelerometers in several places, so up to the bedrock level, because for them, at many places they could get the bedrock level at deep surface with some petroleum related agencies where they did the exploration. So now they are equipped with actual accelerometers put at the bedrock at the same borehole at the top, and now they are actually devising ways to go for far more refined deconvolution techniques. Because of this, they could calibrate their deconvolution technique.
sir, from my side, I would like to ask, means how many boreholes do we need to do for, means how many location we need to choose for this borehole test for a particular region?
Uh, I would like to ask you to clarify the question a little bit.
Means say IIT Guwahati,
Hmm.
how many location you have chosen for this borehole test?
Since it is IIT Guwahati and all the records were there, we actually used whatever was there. So it was around 450 boreholes we have inside the campus. Okay, so at different times when the buildings came out, different boreholes were done, and now the issue is that, let us say, if you are using the borehole record for ground response analysis, okay, so when you are really doing a local scale ground response analysis, so it depends. It we say that wherever your we say that you divide it into a grid of 10 by 10 meter. Okay, so as per the total provision, for each 10 meter you should have one borehole but repeated for two instances, because again borehole excavation and the tests all are uncertain, right? So for our case in the IIT Guwahati, let us say for this particular block where I am sitting right now and delivering, for this particular block itself we had 10 boreholes. So we were in a better position. But if nothing is there and you have to do, then at least go for one borehole for one 10 by 10 meter grid. But then this also is very fine borehole investigation I'm talking about. Then it depends upon your wallet, how much you have the fund. If you have only one borehole fund, go for it. Whatever is there is fine. Okay.
Okay. Next question is from Rajesh Sheikh. What is the solution to prevent such a huge dip slide? I think you have answered already.
Uh, I really did not answer that, because see, for answering that we can sit for another session. So slope stabilization is a part where actually we work a lot, and depending upon the depth of slide, depending upon the velocity of slide, depending upon the constituent of the sliding material, there are various innumerable ways to tackle this problem. So if it is simply say deep slide, let us say it is only soil with some rocky material what is coming up, so basically you can go for starting from the toe, you can go for gabion or flexible type of protection. Then depending upon the soil constituent, you can give a erosion cover with very good drainage. Okay, so finally whatever you do, drainage is the most important counterpart. Water is the culprit. Throw away water, things are going to be stable. Okay, but this question does not have very direct answer. We can sit for another session for that in total.
Okay. Next question is from Vishwajit Thakur sir. In a place like Kolkata, where groundwater table is generally high, authorities are imposing rainwater harvesting through groundwater recharge. What could be the likely effects from soil strength point of view?
Okay, see, the issue is that first of all, we have to understand that the groundwater table being high and low at a place, first of all, it came naturally. Okay, so there is the issue when we started putting barriers to that. Okay, now we are talking of harvesting because we want to bring it higher, right? So we want basically to recharge more water. Obviously, if there is water, so in a very crude sense, your soil strength is bound to go low. But see, that is fine, because you will be designing based on that. It is not readily the issue that whether you have a low soil strength or a high soil strength. It is the issue what design you are using in order to tackle that problem. Do you need ground improvement or not? Do you need to have certain improvisation in your basic foundation engineering design or not? Because groundwater table being higher, we cannot do anything about that. In Guwahati, the groundwater table is actually at 1 to 1.5 meter. Anywhere you dig, the groundwater is going to come out. Okay, but then your design has to be in such a way. Definitely, it has the effect on bearing capacity. You will find in Kolkata, especially the Rajarhat and those filled up areas, the bearing capacity is anyways low. Go for deep foundation system, go for sheet pile protection systems, go for any sort of ground improvement where water from the foundation area can be automatically ejaculated over the time. PVDs in big projects might be a help, and in Calcutta people have used PVDs, stone columns, PVDs, all these things help.
Next question is from Abhishek Mondal. In calculating CRR by seed method, if the N160 CS value is around 34, the CRR value trends to infinity. So is there any limit on the N160 CS value for which the particular equation becomes valid?
Yes, so the answer lies in the question itself. See, something going to infinity cannot be used in calculation. So that itself indicates that there is a limit. And yes, there is a limit for any empirical and semi-empirical expression. See, this thing what we use N160 and CRR, it's not a mechanics-based equation. There is no theoretical proof for that, right? Somebody somewhere, let us say Professor Idris actually, somebody somewhere have done this test over certain type of soil, and many people have repeated for other type of soil which might be similar or dissimilar and come out with certain value. But that does not mean that you can blindly use that semi-empirical expression in this particular case. If your semi-empirical expression is giving desired value, you yourself know that it is not going to work out. There are many papers related to this as well, which talks about this limit of this CRR condition with N160, and that's why in many cases nowadays this N160 is actually replaced directly by the strength parameter itself. See, N1 ultimately is SPTN value, right? It has so much of uncertainty in it that we cannot imagine that whether the semi-empirical expression considered how much percentage of uncertainty, right? So all those being in picture, any empirical, any semi-empirical thing will have their own limitation. We have to understand that, and as he found out it is going to infinity, it's definitely not working. So that means something else has to be done or something has to be used. Literatures are there. For that, you can search the literature for the modified seed Idris characteristic for this CRR with other parameters. Energy-based characterization is there.
Next question is from Abhishek Mondal. For finding liquefaction susceptibility of fine-grained soil as per Wang, 4 criteria need to be satisfied, comprising of LL, FC, NMC, and LI. Now, all these 4 criteria need to be satisfied simultaneously.
If you get to satisfy simultaneously, then you are in a utopian world. Okay, so it is not going to happen. So there is all these criteria. See, whenever we talk about this word criteria, you will see even in the code, it is either criteria or guidelines, as the word mentions. Okay, so somewhere you have to do a trade-off, because all these characteristics again comes from experimental understanding. Okay, for example, as I was telling that we have developed a liquefaction criteria for Brahmaputra sand, gave out a 5 criteria system. Now, do you think that if we do this same test for Ganga sand, it will all these criteria will satisfy? No, because Brahmaputra sand has their own particle size distribution, which is much different from the Ganga or the Yamuna sand or the Ottawan sand or the Innor sand, right? So again, all these expressions, whatever comes out as criteria, all depends on the initial characterization of the soil, what has been done. So in most of the cases, all these criteria will not be satisfied. Okay, so whatever is satisfied is fine. Whatever is not satisfied, rather we need to put importance to that by checking with how much deviation it is not satisfying. Okay, how much tolerance is there. If it is say within 2%, 3%, it's all fine. That uncertainty was probably there in the initial experiment even. Correct. So the amount of deviation, if it is high, then again you have to look at whether it is a anomaly or whether it is a repeated deviation. If it is an anomaly, then you can work out. If it is a repeated deviation, that means for your soil, that particular criteria by Wang is anyways not at all going to get satisfied. So start working like Wang and bring out a new criteria for your soil. At least we did for our local sand here.
Yes. Next question is from Rajesh Sheikh. Slope landslide hazards. Is there any correlation between the strength parameters?
Absolutely. Absolutely, there is correlation. So as I was mentioning in one of the slides that we had worked with different type of parameters in the same slope by using uncertainty and random field. So each parameter combination, when you change, you will see a certain different landslide with different characteristic. Now from those things, you have to find out that threshold combination of parameter beyond which there will be predominant landslides, and you have to work for that. So strength parameter is probably one of the most governing criteria for landslides. Only thing we have to keep in mind, if you are dealing with rainfall induced or let us say seismicity induced where water pressure is there, so how the strength characterization or how the strength parameter is changing with the moisture content, so or water content, that has to be kept in mind.
Next question is from some Gorib Admi. Is there any research work going on towards converting seawater into land?
Sorry, once more, is there any research?
Is there any research work going on towards converting seawater into land, beneficial for humans, as there is shortage of land residential purpose?
I must interrupt here. I don't think this question is very relevant. Let us go to the next
I
question.
will just answer. I will just answer. This is since this is a very interesting question actually. Just to mention, a huge research is going on. So we, as a, if you visit my website, you will see that we have now framed a Australian Indian water center where the main target is coastal reservoirs. Okay, so these coastal reservoirs will actually help in tackling this problem of seawater into land, and a huge amount of fund and research is going on. I would just I just request the person who had put up the question to see the very latest and recent book on coastal reservoirs by Professor Sitaram. So we are working on those. We are working on those things, and it is going to be a substantial research in India in the coming 10-15 years.
Again, next question is from Kim Jong. Sir, all inverse problems are inherently ill-posed and multiple solutions can satisfy your... Oh, sorry, I have got this question again. Sorry.
I think this was done.
Yes, sir. Next, next question is from Rinal Homik. Using only 24 geophone, how you able to get VS at a high depth of around 125 meter?
I would just I told in a very brief manner. I am clearly understanding that that description what I have given will not explain this satisfy this query. I would just request the person who put up the question to visit my website and see that corresponding research paper which we have published. All the details are there. So the basic criteria or the basic technique which we used is called dispersion image stacking. In all the research papers which we have published, a very vivid description of the same has been given. Okay, so dispersion image stacking, that is the key word here, and I would tell Mrinal to basically look into those papers, because otherwise it will be difficult to explain right now.
Next question is from Partho Gupta. The soil is soft and very sensitive, but frost line present at some depth. Then is it possible to apply PVDs?
When soil is soft and sensitive, and what is present? Frost line.
Yes, frost line.
Okay, so I think the question maker is trying to put the soils in the frost zone into picture. Frost line means I would take maybe in the frosted soil. So PVDs will work only when there is a water in its fluid form. Okay, now driving of PVDs is not a problem. Okay, if there is a frost line, driving of PVDs is not a problem. The PVD driving rigs and mandrels which we have is just like our SPT mandrels. Okay, so that is not a problem. But then if there is the problem of frosting pertinent in that particular region, the PVDs anyways will not function. The water will be basically frosted outside and inside the PVDs. Okay, so that will not help anyway. So in general, PVDs we avoid in the frozen ground conditions. There we have other good ground improvement techniques in the frozen ground situations.
Okay, sir. I'll just like to interrupt you. We are
Yeah.
actually running out of time, so we have
Okay.
to conclude the session. Definitely it was not possible to put forward all the questions due to the shortage of time. We really apologize for this, but
So
we have to conclude.
anybody can put the questions later also to my mailbox or something. It is all fine.
Okay, sir. Then means I can I share the mail ID to all the participants?
Yeah, yeah, yeah.
Okay, okay, okay.
It is already there.
Okay, 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 okay. Thank you, sir. Now we have to end the session. Before concluding, I would like to propose the hearty vote of thanks to our distinguished speaker, Dr. Arindam Dey. I would also like to express our profound gratitude to our principal, Dr. Ankur Ganguly, and our HOD, Dr. Mr. Sheikh Hasim, for the moral support and guidance. I also extend my thanks to the dynamic organizing committee. In fact, we have been very fortunate enough to be backed by a team of very motivated and dedicated people like this. Finally, the participants, we expect your presence and support in our next webinars also. So for right now, take care, stay safe, have a good day. Thank you. Thank you very much.
Yeah. All of you stay safe as well. So thank you again. So my thanks again to Dr. Bishwajit Thakur. Bishwajit Da.
Arindam, please stay in the meeting.